We're going to try and quantify this idea of being an elf power by splitting of primes and extensions of the rationals. We're going to extend the rationals by basically elf roots of A and see what primes split, and use Chebotarev density to get a version there. You needed GRH to get an effective version of Chebotarev density. And the last thing you have to do is a lot of analysis. You have to do a lot of inclusion-exclusion to make sure everything works. And the inclusion-exclusion is where this UN ends up showing up. Because at the end you have to take this limit of the compositum of these extensions will generate. So let's do this. Just so you know where we're going, let's actually do it now. So let's try and figure out what's in TL. So prime P is not in TL. Well, this means P is congruent to 1 mod L. And A to the P minus 1 over L is congruent to 1 mod P. Right? So like as Julian pointed out, for it to matter, we need P congruent to 1 mod L. And to be an elf power, this has to happen. This is equivalent to P splitting completely in this extension. So let's see why. Zeta L, elf root of A. And we're going to define this as FL. So the point is, P is 1 mod L, so the zeta L, so in the zeta L part it splits completely. And since A has an elf root mod P, it also splits completely in the compositum. Is this okay? Mike?
Yep.
All right, so we have our extension for every prime L, we can identify the P which are not in TL exactly as the ones which split completely in this particular extension. And Chebotarev density theorem says that Chebotarev, some spelling of that, depending on who you read, theorem implies the primes which split completely have density 1 over the extension. Why is this? Because
response to it.
And this is a quick application, but the Artin symbol of a prime which splits completely is the identity, and the conjugacy class of the identity is the identity, and so it's the conjugacy class has size 1 over the size of the Galois group. Is this okay? Okay. So this also wasn't so bad. So we have the density of TL. We know that we're just going to look at the intersection. We can take a compositum and of FLs, and again say the primes which have a problem in. Let me stick to this. So now we're going to use inclusion-exclusion and try for a density. So we're going to look at L prime. And then we're going to take some large n. So we're just going to take some finite intersection, and everything's fine. FD is the compositum of the FLs, of any FLs dividing it. The problem is this limit doesn't necessarily, if it exists, it doesn't necessarily maintain equality. If you take the limit on one side, you get an inequality. And this is unpleasant. So up till now we haven't used GRH at all. So it's in the analysis that becomes a little messy, and I'm not going to go into in full detail. In fact, I'm not going to do his analysis at all. But it ends up that he uses an effective version of the Chebotarev density theorem, and then several steps of inclusion-exclusion, breaks up this sum into 4 pieces, I think, at the end to do his analysis, and shows that the limits are equal. This okay? All right, so this is the idea of Artin's conjecture and Hooly's proof. Questions about any of it? All right. Check, check. All right, so now we're going to go into a quadratic analog of Artin's conjecture. And the idea of the quadratic analog is almost exactly what you would think it would be. You have K, I'm going to do a real quadratic extension of Q. A in the ring of integers. And you have to again do a caveat that A is not equal to a unit. Sorry. A is not equal to plus or minus 1 or a square. It can definitely be a unit. And you're going to ask the same question, the density of primes, so that is there a positive density of primes so that the order of A mod P is as large as possible. All right, so the point is, because we're looking at rational primes, and the cyclic order of A depends on whether the maximum that can be depends on whether P is inert or splits in this quadratic extension. And for the rest of this talk, the A that we're going to choose is going to be the primitive root, the primitive unit of the quadratic extension, because this is not plus or minus 1 and it's not a square. So it's one of the simplest, like, universal things you could pick that satisfies these requirements. And then you can ask, what happens mod P? Okay. Some personal motivation for why I've been looking at this is that if you want to study class numbers of non-maximal orders, this is just a digression. If this happens to if class numbers happen to motivate you, you have that the size of the Picard group of some non-maximal order divided by the class number of our quadratic real extension is equal to so let me when I say non-maximal order, let me specifically that it's of conductor P, some prime. You have OK mod OK P star divided by the order. So the point is here, you just have your how P splits divided by what's going on in the order, which is basically forgetting that you're in an extension at all. This number here is basically P plus or minus 1, depending on whether P is inert or not. And then you divide by the rank of the unit group.